Today on How It's Made. Electric baseboard heaters. Nothing but the warm, hard facts. Molded pulp containers. This ain't pulp fiction. Prepared chicken. Passing the buck. And video games. Warning, this report contains graphic scenes. Electric baseboard heaters are inexpensive, easy to install, and practically maintenance-free. Unlike radiators, they're inconspicuous, and they take up very little space. And best of all, you can control the temperature room by room. A baseboard heater is simply wires and a heating element in a steel casing. They make the element using a strip of paper-thin aluminum, 19 centimeters wide. It's lubricated with soap, then goes through a forming machine. A die punches the strip into little squares called fins. They measure 16 by 20 millimeters each and have a circle in the middle. The machine pierces the circles and cuts the fins apart. This machine churns out 600 fins per minute. It stacks them on steel tubes, the lengths of which vary according to the length of the heater. As each tube fills to capacity, a worker takes it away to be wired up. Elsewhere in the factory, meanwhile, they make the heater's casing, using what's known as cold-rolled steel, a flexible type of steel that can be worked without using heat. After a squirt of oil for lubrication, the first die cuts holes for attaching the baseboard to the wall. Then the second die cuts holes for attaching the heating element to the casing. Now the steel travels through what's called the roll former, a machine whose series of rollers successively bend the flat strip of metal, one fold at a time, into the shape of the casing. From start to finish, 20 rollers make 20 bends. The process takes exactly 146 seconds per casing. After the last fold, a computer-controlled die cuts the casing to the required length. The higher the heater's wattage, the longer the casing has to be. Models range from 300 watts, about half a meter long, to 2,500 watts, almost 2.5 meters long. Next, they put a steel junction box on each end of the casing. These hold the wires that the electrician connects to the house wiring. Workers spot weld both junction boxes simultaneously. After a thorough washing, computer-controlled sprayers coat the casings in paint powder. Then it's into an oven for about 20 minutes at 185 degrees Celsius. This transforms the powder to liquid, drying it instantly. After running a red wire for the electrical current the length of the casing, they rig up what's called a linear high-limit temperature control, a safety device that prevents the unit from overheating and catching fire. Gas inside the temperature control expands under intense heat, triggering the device to cut the current. Now they install supports to hold the heating element in place. They're made of satin coat steel, a rust-resistant metal. As the element heats up, it naturally expands. To prevent it from scratching against the metal casing and making annoying noises, they install a heat-resistant plastic bushing. Now they connect the red wire that'll carry the electrical current to the heating element's black wire, capping it with a wire connector. They clip it to the cover of the junction box, easy access for the electrician installing the baseboard. Then they close the junction box cover. At At the other end, they connect the red wire and the black wire to the temperature control wire. This runs the electrical current through the safety device at all times. After a voltage test, they close her up and snap on a panel to cover the element. Being toasty warm is now just an installation away. Molded pulp isn't exactly a household word, but it is a household item. Chances are you've got an egg carton in your fridge that's made of it. This thick cardboard-like material can be shaped into a variety of containers, such as those drink carriers they give you at the fast food restaurants. Farms ship out their eggs in trays called filler flats. These flats begin as recycled paper. Old phone books, newspapers, magazines, cardboard, pretty well any product made of paper fibers. The factory even recycles its own flats that have been rejected by quality control. The raw materials go into what's called the pulper, a giant blender that mashes everything up and blends it with hot water that's 43 to 65 degrees Celsius. The hot water swells the fibers, causing them to break apart. After 20 minutes, they become pulp, a watery mixture roughly the consistency of hot oatmeal. The pulp exits out the bottom of the pulper through a filter that screens out plastics and other contaminants. Shaping the flats is a fully automated process. Formation molds descend into a vat filled with pulp. A vacuum sucks the mushy mixture onto them. Water jets rinse off the excess. Rotating above are transfer molds. They grab the flats off the formation molds and move them onto a conveyor. Before the transfer molds grab the flats, though, a brush applies a water-based lubricant. This ensures the flats won't stick to the molds. It's just like greasing a baking pan. The molds themselves are made of bronze, plastic, or aluminum, depending on how long the factory intends to use them. They're covered with a stainless steel mesh. This mesh ensures an even vacuum through the mold so that the pulp spreads over it evenly. The soggy flats now go into an oven for 12 minutes to dry out. The 205 degrees Celsius heat evaporates the water. This bonds the fibers together, forming a rigid material. After they exit the oven, a device appropriately called an upender flips them up so that they stack into each other. A built-in counting mechanism triggers the machine to section off the required number of flats per package, then compress them and seal them in plastic film to keep the dust out. The factory uses the identical molding process to make 4-cup drink carriers. These too go into an oven to dry out the pulp, but only for 6 minutes, half the time the filler flats need, because this product is smaller and lighter. Automated compactors stack the finished drink carriers. Then workers compress them for packing and shipping. The factory also makes disposable urinal bottles for hospitals. They add chemicals to the pulp to make the bottles liquid tight. These molds are three-dimensional and lined with mesh on the inside. When they submerge into the pulp vat, a vacuum sucks in the pulp. When they resurface, water jets rinse the excess pulp off the bottlenecks, and the vacuum sucks out the water. A spiked conveyor belt transports the bottles to the drying oven. They dry at a lower temperature than the flats and drink carriers do, 176 degrees Celsius, and for a longer time, a half hour. This ensures the chemicals making the bottles liquid tight cure thoroughly. While urinal bottles can't be recycled for sanitary reasons, drink holders and filler flats are recyclable, making them extremely environmentally friendly. In the year 2001, Canadians ate 31 kilograms of chicken per person. Given that rate of consumption, if we had to process the poultry ourselves, chances are we'd be in a rather foul mood by dinner. Thank goodness for chicken processing plants. The chickens arrive at the factory with their feet, legs, and heads already cut off. What's left are the breasts and wings. The slaughterhouse also removed the internal organs. A conveyor belt transports the chickens to the cutting and deboning zone, a bustling assembly line operation. Workers prop each chicken on a cone-shaped stand in order to have both hands free to work on it. Cutting up a chicken properly isn't as easy as you might think. The workers get special training. It's crucial they keep their knives well sharpened and wipe them after every 5 or so chickens. The first cuts remove the wings, starting on one side and positioning the knife horizontally in line with the top of the cone. The worker makes an incision where the wing joins the shoulder, then cuts downward across the back of the chicken. Then a quick cut and twist to detach the wing. It's the same procedure on the other wing. The incisions at the wing-shoulder joint must slice through the tendon completely. Otherwise, detaching the wing is difficult. And struggling with a slippery wing while holding a knife in your hand can result in serious injury. The next cuts remove the skin and breasts. They peel off the skin, then pull on the 2 breasts and make a quick incision to release them. They slice the breasts apart, carefully checking for bones that might have broken off from the carcass and be hiding in the meat. The next cuts remove the tenders, the meat located under the breasts. Workers make an incision in the middle just under the wishbone and down the length of the carcass. This detaches the tenders, enabling the next worker on the line to pull them off. Meanwhile, waiting in the wings are the wings. Workers load them onto a machine appropriately called the wing cutter, a mini Ferris wheel that takes the wings for a little ride, right into a sharp knife that chops them into 3 sections: the drumette, the chubby part with the most meat, the winglet, the middle part, and the wing tip, the pointy part with barely any meat. This factory transforms the meatier drumettes and winglets into frozen, ready-to-eat chicken wings. The first step in that process is seasoning. Workers load the pieces into a giant drum. As the drum rotates, they inject the seasoning, barbecue or honey garlic, for instance. After about an hour, the chicken wings come out evenly coated. Now these freshly seasoned wings go into a gas-fired oven where they bake at approximately 250 degrees Celsius for 8 to 11 minutes. They come out fully cooked and ready to eat. They go into a freezing mechanism for about a half hour, then to the automated packaging department where they're sealed in a bag. These chicken pieces, wings, tenders, and breasts, are prepared differently. After seasoning, they travel through a rotating drum that coats them in a flour and breadcrumb mixture, then into a second drum for a second coat. Next stop, a 40-second deep fry in canola oil, just long enough to adhere the coating. Then from the frying pan into the fire, as they say. Well, into the oven, actually. After 20 minutes at about 250 degrees Celsius, these chicken pieces are fully cooked and ready to be frozen and packaged. They started out a generation ago as simple black and white ping pong games on a TV screen. Today's video games are vivid, sophisticated, and fast-moving, driven by state-of-the-art computer software featuring the latest in high-tech graphics. It all started in 1952 with a Cambridge University PhD thesis on human-computer interaction. The student invented a primitive tic-tac-toe game on a vacuum tube computer, the very first computer game with graphics. A team at MIT designed the first recognized computer game in 1962. Then, in 1972, a Stanford student invented the arcade game Pong, which later became a home video game to play on your TV set. It all begins with the people who form what's called the core team. They brainstorm in meeting after meeting to hammer out the concept, how the game will look, how it'll work. Then they plan out the production schedule, assigning who'll do what, when. They break down the game on paper and color code the components. Then they post them on a bulletin board that'll act as the production's nerve center. Now work on the artistic concept begins. Artists sketch out the characters and backgrounds on paper in a scene-by-scene storyboard. Meanwhile, graphic artists recreate those storyboard drawings three-dimensionally on the computer. This step enables the development team to use the latest in computer animation technology to bring the game elements to life by adding colors, textures, shading, and, of course, movement. After developing a preliminary version of each character, the animators superimpose a skeleton. By manipulating the skeleton, they make the character move. They experiment with different movements until they decide on which ones they'll use for the game. The animators have to design every movement each character can potentially make in the game. That's 700 movements for this main character alone. Once that's done, they flesh out the character's features and costumes to completion. The evolution of the characters from the first pencil drawing to the final version is quite remarkable. Other animators work on the backgrounds, the game's playing field. Once they have a rough version laid out, they refine it by adding details, colors, and textures. To give it depth and dimension, they use virtual lighting to create shading and shadows. To advance the storyline, this particular video game is interspersed with 1-minute animated movies. These segments, called cinematics, are animated in high resolution to produce a top-quality image. The interactive game, on the other hand, is in low resolution because computers can't process high-res images quickly enough for fast-moving play. So the animators have to create every character twice in both high and low resolution. Meanwhile, for the cinematics, they animate the storyboard using rough draft characters. This is simply to calculate the timing and to map out a clear path across the backgrounds, so that the characters don't collide with the scenery. To make the cinematics action look realistic, they use a technique called motion capture. The animators videotape themselves performing the action, then use animation software to reproduce it on the computer. Computer programmers create the video game's menu settings, among other features. Computer engineers design the artificial intelligence, the brain that runs the game. It's made up of thousands of computer codes. For the cinematics, actors record the characters' lines in a sound studio. An audio technician mixes the voices with music and sound effects and synchronizes everything with the action. Now they take the video game out for a test drive. Do the characters move the way they're supposed to? Do they go where they're supposed to? Or do they run into trees and walk through walls? This is the development team's last chance to rid the game of any bugs. After that, the company can finally market this video game and hope it becomes a hit. If you have any comments about the show, or if you'd like to suggest topics for future shows, drop us a line at www.howitismade.net. The How It's Made crew vehicle is courtesy of Subaru Canada.